Okay, so we are back for part two of the previous video. So as I mentioned, we're going to talk about the converse of the theorem that we studied in the previous video and also a corollary. So let's read the converse of this theorem. It reads, if a line in the plane of a circle is perpendicular to a radius at its outer endpoint, then the line is tangent to the circle. So basically in this one, we know that the radius and this line are perpendicular to each other at point Y. And what that's telling us, or what we can deduce from that, is that that line, so in this case line AB, is tangent to the circle. So basically just the opposite of what we learned in the previous video. Now, from the converse of that theorem, we can look at this corollary. And the corollary reads, tangents to a circle from a point are congruent. So I want to take a look over at the diagram and just kind of explain why this is true. So basically what we want to show is that line segment AB and line segment AC, let me highlight those for you. That line segment AB and line segment AC are congruent. So that's what we want to prove. So I'm just going to do kind of a quick informal proof of that for you right now and why that would be true. So if I were to draw in the radii, D to B, and then C to D, we know a couple things already. One is that AB is tangent to the circle at point B, so there'd be a right angle formed right here. And then the same thing's true with the intersection of DC and AC. There's a right angle that's formed. And that's from the theorem that we just talked about, the converse of the theorem that we talked about in the previous video. What we also know is that all the radii in a circle are congruent. So we know immediately that these two radii are congruent to each other. And then if we draw a line segment from A to D by the reflexive property, that segment is congruent to itself. So triangle ABD is congruent to triangle ACD by, in this case, hypotenuse leg. So by CPCTC, AB is congruent to AC. So again, just kind of a quick informal proof to show you why that corollary is true. So now what we're going to do is apply the converse and the corollary to solve examples 2 and 3. So let's take a look at example number 2 first. What I'm going to do is I'm going to actually name the centers of these circles. So I'm going to call this B, call this L. So if we look here, circle B, you see that we have this 90-degree angle at the point of intersection of line PT and circle B. So that means that PT is a tangent. Now the same thing can be said for SQ. So SQ is going to be a tangent to B and L, and then PT is going to be a tangent to B and L as well. So basically what's happening here is that this diagram that we're seeing in example number 2 is pretty much exactly, or is illustrating pretty much exactly what we see up here. So if that's the case, here's what we know. Since QR and PR start from the exact same point, so they start from point R, and they're both tangent to the circle, that means that segment PR has to be 13, which is true because of the corollary that we just looked at up from above. The same thing can be said from R to S and from R to T. So RS is tangent to S, to circle L. RT is tangent to circle L, and they both originate from point R. So this would have to equal 9. RS would have to equal 9. So if we're looking for the total length of PT, we'd have to add 13 and 9 together. So 13 and 9 is 22. And QS, the same deal. We'd have to add 13 and 9 together, and that's also going to give us 22. Example 3, Similar deal here. We have a circle that is inscribed in that polygon. So if you look, here is the point of tangency, here is another point of tangency, and these are roughly where the points of tangency are, right around there. So the same idea that we applied to solve example 2 can be applied here. So I'm going to call A, B, C, D. So I'm just labeling the points of tangency to give us line segments to talk about. So grab the highlighter real quick. So if we look, RA and RB are going to be the exact same length. And again, this is based off of the corollary that we just talked about. And then the same sort of pattern is going to hold true as we work our way around this quadrilateral. So here, this length and this length are going to be the same because, again, of the theorem from above. PD and PC are going to be the same length. And then SA and SD are going to be the same length as well. And again, all for the same reason. Those segments are all tangent to the circle, and each pair originates from the same point. So now we just need to find the length of SP. So SP, again, let me grab the highlighter real quick, is this total length right here. So 24 plus 15. So SP is going to equal 24 plus 15, which is 39. And then RQ, again, this is kind of a little messy over here, so I'll try to use blue for our highlighter pen here. This is what we're looking for in blue. So RQ is 23 plus 17, which is 40. I'm going to do a couple more examples, and then I'm going to have you guys try some practice and check your answers on an answer key that I posted. Example 4, you're trying to find the length of AC, so I'll highlight that for you. We're trying to find that length right there. And this one is pretty straightforward, as long as you know that the radii of a particular circle, they're all the radii are going to be congruent. So in this case here, this length, so the distance from A to the other circle B where they're tangent is 3 units. This segment right here is a radius of the circle, so that's 2 units. This one's also a radius, so that's 2 units. And then in the smaller circle, the segment that I highlighted in purple is a radius as well. So we're going to add up all those lengths. So AC is going to equal 3 plus 2 plus 2 plus 1. So it looks like that is going to equal 8. If my arithmetic is correct, 5 plus 3 is 8. That's correct. All right, and then finally, one more example. Example number 5. All right, so we're told that CB and CD are tangent to circle O at B and D respectively, and we want to complete the following. So we know that OC is equal to 15. I'm going to label that on our diagram. And that OB is equal to 9. And we want to find the length of BC. All right, so this one's actually similar to one that we've done already, an example from last class. So remember, BC is tangent to circle O at point B. So the radius and that tangent are going to form a 90-degree angle at that point. So it appears here to find X, we're going to be able to apply the Pythagorean theorem again. So we've got X squared plus 9 squared equals 15 squared. So again, we'll go through this. X squared plus 81 equals 225. We'll subtract 81 from both sides, and that's going to give us 144. Take the square root, and we're going to get X equals 12, which I believe are the same exact numbers as the example from the previous video. That's all right. All right, so you're going to end up completing the rest of example number 5, parts B through H, and that's what you'll submit as your evidence of learning for part 2 of this section. As always, email me if you have any questions or concerns. I hope all is going well, and we'll talk to you in